Now that we've discussed the dot product, it makes sense to introduce vector projections. Vector projections come up a few times in the course, and this is just a short lesson. We define what they are, how to calculate them, what they look like is actually important as well. So a projection is kind of like a shadow, okay? Something you get when you draw perpendicular lines onto whatever it is you're projecting. So for vector projections, a projection, you can project one vector onto another. So in a way, it's kind of like an operation. Here I'm going to talk about the projection of vector x onto vector y. And I've drawn vector x and y here with angle theta, assuming angle is acute and then giving an obtuse example as well. So like if you just look at the picture, the projection, imagine drawing lines that are perpendicular to y from x, like this, kind of like a shadow. Okay, the vector formed from here to here, that vector right there is actually the projection. And there, I think you can see it a little clearer now. So we're going to call that, I'm going to call this point O and this point N. So that in this picture here, we can say that the projection of x onto y is actually just the vector that goes from O to N. And now what we'll do is we will look at how it is that we calculate that. I'm going to leave this example alone for now. We'll just come back to it. So the easiest thing to do is to actually start by talking about, okay, well, how do we figure out how long this vector is? What's its magnitude? Okay, so although the projection will be vector ON, we're going to start by finding the magnitude of ON. And the reason we're going to find the magnitude of ON is because vector ON is going to have the same direction as y, so it's not a difficult thing to determine its direction. If we look at the picture here and we look at the cosine ratio, we can see that the cosine of theta will be equal to the magnitude of ON divided by the magnitude of x. Okay, adjacent over hypotenuse in this little right angle triangle, which means that vector ON, the magnitude of ON, is really just the magnitude of x times cos theta. Okay, you could probably get that all in one step. Sorry if that's a little jam there for you. So that means that ON is the magnitude of x times cos theta. Now I'm actually going to take and I'm going to say, okay, well, let's look at this picture here too. So in this case, imagine that the vector is, the angle between the two vectors is greater than 90 degrees. So what does that mean about your projection? Well, now it just means that your projection instead goes in this direction right here. So ON now has this direction right here. So in this case, if the angle is greater than theta, we would say ON doesn't have the same direction as y, it has the opposite direction as vector y. Now looking back here, everything works here for the magnitude of ON, except the cosine of theta would now be negative, okay? Which is okay, but we shouldn't talk about the magnitude of a vector being negative. So we're going to throw some, these are not magnitude signs. Those are actually absolute value signs around the same. Look, in this case here, just drop the negative because we can't have a negative magnitude. So the magnitude of ON does need to be a positive number. Okay, from there, we're going to do something a little bit interesting. We are going to take this and we are going to multiply by the magnitude of y over the magnitude of y, which is really just multiplying by 1, of course. There we go. Now, why did we do that? Well, if we were to now rewrite this, just so it looks a little bit different, we can say that the magnitude of ON, which is the magnitude of the projection, is equal to the magnitude of x times the magnitude of y times the cosine of theta, all divided by the magnitude of y. Now we still do need those absolute value signs to take care of the fact that the cosine might be negative. Notice that this is always positive. The magnitude of a vector is always positive, so it doesn't matter that I can put that inside the absolute value signs. It doesn't change anything. Now the reason I've done this, you probably can guess, is that this is the dot product. So now we can say that the magnitude of the projection is really the dot product divided by the magnitude of y. And there you go. So there's a formula that gives you the magnitude of the projection, okay, which is just the length of the projection. It's very similar to the dot product. Notice that these are not magnitude signs. Okay, these are absolute value signs. Okay, to take care of the fact that the dot product could technically be negative. In this case right here, okay, where vector x, okay, is here, then you would have a cosine ratio that's negative, and so you would calculate this as a negative. We don't want it to be negative because it's a magnitude, so it can't be negative. So although I haven't quite defined the projection, since the projection is a vector, I've found the length of the projection. So that actually is a useful formula to write down. We could say the magnitude of the projection of x onto y. We don't really have a better symbol other than writing that. Is equal to this formula right here. The absolute value of the dot product between the vectors divided by the magnitude of y. Okay, continuing with this idea, we have the magnitude of ON, but we actually want to know what vector ON is equal to. So what we could do is we could say that ON is really the magnitude of ON times a unit vector in the direction of y. So once we have the magnitude of the projection, we know it has the same direction as y, or possibly opposite direction. We'll worry about that in just a second. So what we could do is we could say take this vector, take that magnitude, and just multiply it by a unit vector that has the same direction as y. And since the unit vector has a magnitude of 1, it doesn't actually change the vector ON other than giving it the right direction. It's kind of like you're basically saying, oh, okay, the magnitude of ON is that I know that this is 5 long. Oh, okay, well, if it's a vector that's 5 long and then multiply it by a unit vector in the direction of y, and you'll get the actual vector ON because it'll have the direction and the correct magnitude. So what I'm going to do is I'm going to replace this ON with the formula that I have. Okay, just like so. Of course, any unit vector, y for example, the unit vector y is really the vector y divided by its own magnitude. Okay, remember normalizing a vector? Okay, you might want to review that. That's how you normalize a vector, by taking a vector and dividing it by its magnitude. And so we can do the same thing here. We replace the unit vector y with vector y divided by its magnitude, like so. And that sort of simplifies to this right here, the magnitude of y squared, the dot product, and there you have it right there. Now, something important to notice. This gives you vector ON, and notice I've actually dropped the absolute value signs here. And that I want to do that actually, because now what happens, interestingly enough, is if the dot product is negative, I actually want that negative value, because I want, if I have this picture right here, okay, where the dot product would be negative because the cosine of the angle, the cosine is negative since it's greater than 90, I want the vector ON in the opposite direction. So I want the projection in the opposite. So now all of a sudden, although here I didn't want the negative value because I couldn't have a magnitude that's negative, now I do want the negative value when it arises because I want the vector to have the opposite direction of y. So here is your formula for the projection, just to sort of rewrite it. The projection of x onto y is given by the formula x dotted with y. Okay, and then this would be scalar multiplication, okay, since that's a scalar and that's a vector, divided by the magnitude of y squared. Just like that. So we kind of have two formulas for projection. One gives you the actual vector, and the other one gives you the magnitude of the projection. So depending which you want, you can use either equation. I mean, technically, you could always just use this equation. Then if you want the magnitude, just find the magnitude of the vector that you get. But since we had to do this first, and it's simpler, it's often common to work with this equation as well. Okay, let's look at an example here. Now, I should point out that when you're using these formula for calculating projections, it's almost always because you have vectors in algebraic form. If I had geometric vectors, like vectors described using a picture, I probably have, the two vectors, I probably have their angle between them and their magnitudes, and calculating the projection, which would be, this vector right here, is just a geometry question. You've got the angle, you use the cosine ratio, you can figure that out easily enough. So here we have algebraic vectors. So let's start by writing down the formula that we need to find the projection. Okay, so the projection of A onto B is A dotted with B times B divided by the magnitude of B squared, which in this case we have vector A 2, 0, -4. We're going to dot that with 1, 3, 8. We're then going to multiply that by vector B, which is 1, 3, 8. Okay, there's only one way to do this. We obviously need to do the dot before, but it's still not a bad idea to throw some brackets there. Divided by, okay, now the nice thing is the magnitude of a vector squared means the square root and the squared sign cancel out. That's very common that we see formula with that. 1 squared plus 3 squared plus 8 squared. Again, square root squared all cancel out. Okay, doing the dot product first. 2 times 1 is 2, okay, plus 0 minus 32 gives you negative 30. So we're going to scalar multiply that with the vector 1, 3, 8. We then do 1 squared plus 3 squared plus 8 squared, which gives us 74. Okay, do the scalar multiplication, divide by 74, you get the final answer, which is going to be negative 30 74ths, negative 90 74ths, and negative 240 74ths. Of course, all of those could be reduced. And there you have it, the old 74 divides by 2. So there's the projection of A onto B. Now in this particular case, if we were to look at the picture, since the dot product was negative, we know that actually the vectors must have looked something like this, where this is vector A and this is vector B. And then we calculated our final projection of A onto B, which would be a vector that looks like that right there. Having the opposite direction that B does. And you can kind of see that here. I mean, 1, 3, 8, all positive, so not a big surprise that our projection would all be negative values as the opposite direction, so it would have to be. In this next example, I'm just pointing out that there are some cases when you just want the magnitude of the projection, you don't care about the actual vector, in which case it's just a little bit less work. I can use the first formula that we came up with here. That's that it will be the absolute value of x dotted with y divided by y. Notice that the projection operation is not commutative. The projection of x onto y is not the same as y onto x. So it's just a matter of figuring out the dot product, taking the absolute value, that dividing by, let's see, y, the square root, negative 1 squared, plus 2 squared plus 2 squared. Okay, and let's see, let's do this part here first. On the bottom, that's going to be 4 plus 4 is 8 plus 1 more is 9. We get 3. And on the top, we get 0 times negative 1, which is 0, plus 2 is 4. So we just get 4/3 here for our answer. If we wanted to actually find the projection, then we could take the 4/3 and we could multiply it by a unit vector in the direction of y, which we'd get by taking y and dividing it by its magnitude. Or we could just use the other formula that we used in the previous example, which is this one right here. Okay, in this last example, I said find the projection of the vector v onto the basis vectors I, j, and k. So if you remember, I, j, and k, I goes in the direction of the x-axis, j goes in the direction of the y-axis, and k goes in the direction of the z-axis, and they're each unit vectors. So that means that, for example, vector I just has the coordinates or the value 1, 0, 0. So to start with, I can do the projection of v onto I. That will be v dotted with I times vector I divided by the magnitude of I squared, if I just use that formula. Now, there's a few things that we should notice. The magnitude of I is 1, so we're going to get a 1 here. So really, we're taking the vector v for negative 8, 1, dotting it with 1, 0, 0, and then multiplying that by 1, 0, 0. Brackets in there to make that, and then the bottom is just equal to 1, so we don't need to worry about that. Okay, so do the dot product next. 4 times 1 is 4, and then you get negative 8 plus 0, which is 0, plus 1 times 0, which is also 0, just gives you 4. So you get 4 times 1, 0, 0, which is the vector 4, 0, 0. Now let's just think about that for a second. That shouldn't be surprising at all. You've got some vector v, let me just draw it here, like that, okay? It should make sense that if you were to project this onto vector I, which would be right here, that all you're going to get is the x part, okay? The 4 here, you're going to get the x value of this vector, okay? That should make sense. In fact, these lines should sort of continue, you know, all the way the length of the vector like that. So really projecting on the, if we just think about it geometrically, we should be able to figure out what we're going to get here. It's just going to be ij, the ij and the k values. So for example, the projection of v onto I is 4, 0, 0, whereas the projection of, let's do projection of v onto k is just going to be the y number, so negative 8, and it will be negative. And then the projection of v onto, oh sorry, that's the projection of I onto j, not k. And the projection of v onto k would just be equal to 0, 0, 1. So again, you could use those formulas if you want to, but it doesn't take much convincing to realize the answer is kind of right there in the vector. In fact, that's kind of what a vector is. It's represented, its vector numbers are in fact its projection onto the x, y, and z axis. So the formula is right there. You can always use it, but in this example, it's not necessary. Okay, projection. There's really a nice notation that's kind of just the best to kind of write. Proj for short of v onto j is fine. You can take a look at how your textbooks writes that too, and there's a few questions for you to try so that when you see projections coming up in the next few lessons even and going into the next unit on vectors that we look at, you're going to find that that we do use these projections from time to time.